Hello students, welcome to Sri Jayendra's Rank Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 1 of a unit, Waves. Let's begin with today's class. This is the introductory session of a waves. So let's begin. Look at this point and what could you say about the state of the water? What do you understand? Yes, we generally say that it is at rest. Now let's look at this picture. Yes, it is the same pond, but now that water has been coming from that fall too, and at a location, look at this position, at a location where this fall is adding the water, a certain ripples has been formed at that point. It is the same situation. It is the same situation when you drop a certain pebble or stones at a certain point in the pond. So at that point, a ripple is going to be developed, or we can say that a certain disturbance can be developed at that point, and that distance or that disturbance, does it stay there only? Is that disturbance confined to that place only? Is it? Or you can see that a smaller circle has been formed, and that circle we think that that circle is going to be spread out. Yes, from smaller circle to a larger circle. So it spreads out in the form of the circles from the point where the water surfaces gets disturbed. I hope this is clear. So, what have you observed? What have you observed when you put a cork or a piece of paper on the disturbed water surface? The piece of cork starts oscillating up and down about the mean position, and it does not move forward. So, what do you understand by this? We can say that a disturbance is created at a point, and that disturbance moves forward, but that disturbance move forward, but not the particles of the medium will stay at that position only, and they are not going to move anywhere. I hope this is clear. So it is the disturbance that travels through the medium due to repeated vibrations of the particles of the medium about their mean position, and the motion is being transferred from one particle to another without the transport of the particles of the medium. So if we understand that what is the quantity that is transferred during the propagation of the wave, yes, our answer would be an energy that you have learned in ninth class too. But one more other than the energy too, and that is the momentum. That when and when any wave propagates, it carries or it transfers two quantities. It transfers two quantities. One is the energy, another is the momentum. I hope this is clear. Is it? Is it clear? Great. So, next question is, do sound and light form waves? Do they can be categorized as a waves? Answer would be absolutely yes. Next, does sound require a medium for propagation? Can you talk on the moon without having any devices? Can you talk in the vacuum without having any devices? Our answer should be no. Why? Because without medium, sound cannot propagate. But let me ask you the same question for the light wave. So the question is, does light wave require a medium for the propagation? Our answer would be a no. Light can propagate even in a vacuum. Yes, you have studied this in class 10. So it means, does all the waves require a medium for the propagation? Again, our answer should be no. That there are certain waves that only require the medium for propagation, and not every wave require a medium for the propagation. So let's look at certain quick questions. Which of the following waves requires a medium for propagation? Electromagnetic waves? No, they don't require medium. Ultraviolet waves? No, they don't require a medium for propagation. Light waves? Absolutely no. Sound waves? Yes, they require a medium for the propagation. Next, what is transferred due to disturbance of medium? It is the energy. Yes, momentum is not the option, but if it is there, this both should be an answer. Please keep this in mind. So they will transfer energy and momentum. Next, which wave propagates in both medium and vacuum? Sound waves? No, it can only travel when medium is there. Mechanical waves, again same thing. Light waves, yes, this can transfer, this can propagate through both. If medium is there, it will use it. If no medium is there, it does not require. I hope this is clear. So let's discuss types of the different waves. Let's have a look to the types of waves. So these are the different types of waves, and broadly I can classify them into two segments. One of them is the electromagnetic waves and the another is the mechanical waves. This electromagnetic waves is the part of the 12th class, and this mechanical waves, it's a part of the 11th class. So today and onwards for this session we are going to discuss about the mechanical waves. And mechanical waves could be again classified into two kinds. One of them is the progressive waves, another is the stationary waves. And progressive wave again in two segments. One of them it's the longitudinal waves and another is the transverse wave. So we are going to see this one by one, each category. First, let's discuss the electromagnetic waves. What is it? We can say that it's the waves which travels in the form of oscillating electric and magnetic fields are known as the electromagnetic waves, and such waves don't require any material medium for their propagation. So these are also known as the non-mechanical waves. And all electromagnetic waves that travel through the vacuum with the same speed c as that of the light wave, and speed of the light could be given as c is equals to 3 into 10 to the power 8 meter per second. So all these waves travel with the same speed of light. Examples of the electromagnetic waves, they are the radio waves, microwaves, x-rays, visible and UV light. This all are the examples of the electromagnetic waves. Next, it is the mechanical waves. They are the waves which require material medium for the propagation, and these waves are known as the mechanical waves. These waves are also known as the elastic waves because they depend on the elastic properties of a medium. Examples, they are the sound waves, water waves, seismic waves. So seismic waves, they are the waves emitted at the time of the earthquake. So these are known as the seismic waves. So these are the mechanical waves, and they require a material medium for their propagation. If they found the medium, they can travel or they can propagate. If they don't found a medium, they are unable to propagate. Now let's take how they use the medium with the help of the propagation of sound wave through air. Let's understand that a small region of air is considered as a spring, and so it is connected to the neighboring regions of the spring. So when sound wave propagates through air, it compresses or expands a small region of air. And when they compress or expand a small region of air, this can produce a change in the density, and if density changes, a pressure even changes in that region. Let's understand that we are using delta P as a change in pressure and delta rho as a change in density. So what pressure is? Basically pressure is the force per unit area that we understand. It's F by A. So restoring force, and the restoring force is proportional to the change in density that we understand. Yes. So in this case, the change in density is similar to the extension or compression in the spring. Yes. So as you stretch or compress the springs, they are having a change. They are having the change in the pressure. They are having the change in the density. Same thing happen with the air as well. So the region at which the density is less, this is what we call as a rarefaction. And if the region is compressed, its molecule tends to move out and enter into the neighboring region, thereby increasing the density and produces a compresses in that region. So the air of the surroundings rushes the rarefaction region, and this will shift the rarefactions to the neighboring region. So compression and rarefaction move from one region to another, and the atoms, or we can say a group of atoms or group of atoms are in equilibrium due to the forces from the surrounding atoms. So if one of the atoms displaces from its equilibrium position, or restoring forces developed that we have learned, and the disturbance produced by the force travels to the next atom, and so on. So thus the wave propagates through solid as well. So I hope you have done this in your school classes too. This is just for the revision purpose. So I hope you understand this. Is it? Great. Let's look at certain quick questions. The region at which blank is maximum is called as compression. Yes, in that region density is maximum. Next, the region at which the density is minimum. Yes, density region, it's a rarefaction. Next, the speed of light in vacuum. Yes, it's a 3 into 10 to the power 8 meter per second. I hope this is clear. Now let's understand what transverse and longitudinal waves is. So let's first look at the transverse waves. They are the waves in which the particle of the medium oscillates perpendicular to the direction of the propagation waves, are known as the transverse waves. So basically it is the situation something like this, that let's suppose this kind of wave is there. So its direction of propagation, this is the direction of propagation, and this is the direction of oscillation. I hope this is clear. So this is in y direction and propagation is in x direction. So they are the waves in which the particle of the medium oscillates perpendicular to the direction of propagation of wave, and these are known as the transverse waves. Yes. So it's a horizontal string with one end fixed to a rigid support and the other end is held in the hand. And this this kind of waves can be developed, that this is the situation that if you have tied up strings one end at this rigid end and this is in your hand, and if you're giving a jerk over here, then it can produce this kind of wave, something like this. Yes, this is the string wave, and this form of wave is the transverse wave. I hope this is clear. So this kind of pattern can be developed, and if this kind of pattern can be developed, we can understood the different segments of this pattern. So the maximum displacement in the upward direction is called as a crest. This is what we know as the crest. And in the downward direction, this is what we call as a trough. And crests and troughs are formed alternatively. Every particle of the medium in a transverse wave undergoes an ascension, but the phase of the particle differs and their amplitudes are equal. I hope this is clear. So the velocity of the particle is maximum at the mean position, and it is zero at the extreme position, and it is the same thing as we learn in the SHMs. Yes, and these waves are possible in solids and strings, but not in the fluids, because they cannot sustain the shearing stresses. Yes. Examples, these are the light waves or waves on a strings and roads. Yes, etc. Next, let's look at the longitudinal waves. First, let's understand very carefully compression and rarefaction. If you have not understood, look at the region. Yes, look at the region of the this crest. That when you observe the region of the crest, you find that it is a region having higher density. And if you find out the troughs, then it is the region having lower density. I hope this is clear. Is it clear? This is how any wave travels. I hope you understand now. Yes, yes, great. So it is the waves in which the particles of the medium oscillates along the direction of propagation of wave. This is what we call as a longitudinal waves. So let's consider a long cylinder which is closed at one end and having a movable piston. And if a piston is moved suddenly down, a small layer of air just near the piston air is compressed and the layer moves down and compresses the next layer. So a compression travels along the cylinder to the other end, and if the piston is moved upward, the air layer adjacent to the piston is rarefied, and as a result a pressure decreases. So the air from the next layer moves in to restore the pressure, so the next layer is rarefied. So in this way a pulse of rarefaction moves upward. If we continuously push and pull the piston, then a sinusoidal sound wave travels in the form of alternative compression and rarefaction. And at the compression the pressure or density of the medium is maximum, and at the rarefaction they are the minimum. So examples are the waves on the springs or sound waves. So these waves can be propagated through solids, liquids, as well as gases. Best example of this kind is the sound wave. Yes, so it can propagate through every medium. It can travel through solids, it can travel through liquids, and it can travel through gases too. Let's look at certain quick questions. They said the waves in which the particles of the medium oscillates along the direction of propagated wave. Yes, in this particles of the medium oscillates along the direction, they are the longitudinal waves. In the transverse wave, they are perpendicular. Here, it's a perpendicular to propagations. Next, the waves in which the particles of the mediums oscillates perpendicular to the direction of propagated wave are known as the transverse wave. Great. So do you understand up till now? Is it? Now let's study the displacement relation for a progressive wave. So first thing is what progressive wave is. We can say it is a wave which proceeds in the medium without being reflected. This is what we call as a progressing wave, that it will continue moving in a particular direction and it is not going to be came back. That is what we call as the progressive wave. This wave could be longitudinal one or it could be a transverse wave. So plain progressive harmonic waves are there, and as we add the word harmonic, it is having certain special meaning. Let's we look. So if the particles of the medium vibrates about their mean position, then the wave is said to be plain progressive harmonic wave. Let's look at this. Yes, this is the wave that has been developed, and you can see that it is traveling. I hope this is clear. Yes, yes, do you understand this? Yes. So let's understand that the displacement of the particle at in at the origin O and at any instant t, that could be written as, I am here writing in terms of the two position. It's a first is the position, another is the t. I have taken a reference from the origin and at time t, so I can write it's a y is equals to a sine omega t. And let's understand that a wave that starts from the origin and it travels along positive x-axis with a speed v. So at t is equals to 0, the particle is at the origin and it passes through its mean position. So consider another particle p on the x-axis which is at distance x. This is at distance x from the origin O. So the displacement of that particle, the displacement of particle p at any point p at any instant t, can be obtained by replacing t by t minus of x by v. Yes, it's a t minus t naught kind of thing. So if I replace this t in this relation, it would be a y is of xt, that is equals to a sine omega into bracket t minus x by v. If I solve this, this is y xt is equals to a sine omega t minus of omega x by v. Now we can have a one constant that we are having, it's an omega by v. You can see this omega could be equals to 2 pi f, that we understand. It's a 2 pi f divided by frequency. So this is equals to frequency divided by velocity, which is equals to lambda. It's a wavelength, so it's a 2 pi by lambda, and the ratio of the 2 pi by lambda is this is going to be denoted by k. This k is called as a propagation constant, as well as it is having one more name, it's a wave number. So if they said it's a wave number, they are indirectly informing you about the k, propagation constant or wave number. So this y xt is equals to a sine omega t minus kx, or this y of xt is equals to a sine kx minus omega t. This equation represents a harmonic wave that is traveling along positive directions of the x-axis. I hope this is clear. Is it clear? Is it? Great. Now let's look at the certain variations of this relation. We have this relation that y is equals to a sine omega t minus of kx. Yes, so I can replace this omega with 2 pi by t, where t is the time period. So this is equals to 2 pi by t into t minus of k, it's a 2 pi by lambda into x. Or if I took 2 pi as an outside, it is a sine 2 pi into bracket t by t minus of x by lambda. Or if I took this 2 pi by t as an outside, this is equals to a sine 2 pi by capital T into bracket t minus x by lambda into t. But lambda by t, it's a velocity, so this could be represented as y xt is equals to a sine 2 pi by t into bracket t minus of x by v. Also we can have this, it's a y of xt, this is equals to a sine 2 pi by lambda into bracket lambda by t into t minus of x. So these are the certain variations which can be done with the waves. But what we need to do is we need to stick to our basic relations. Let's have a look. I will show you. So from this there are one more variation is, it's a y of xt, it's equals to a sine 2 pi by lambda into bracket vt minus of x. So let's understand that if the initial phase of the particle at O is phi naught, then the equation of wave motion could be represented as y of xt is equals to a sine omega t minus kx plus phi naught. Or it could be y of xt is equals to a sine omega t plus kx plus phi naught. So these two are my standard relation, or we can say it's a master relation for us. We are going to rely on this two only. Yes, whatever the difference, whatever we are going to have, or we have been given in the data, we are going to correct it or modify it according to our standard relation, and then we will do the mathematics. Now one more very important thing is, if omega t and kx has been related with minus sign, it could be my omega t minus kx, or it could be a kx minus omega t, then it means this wave propagates in positive x direction. And if this too, it's an omega t plus kx, or it could be an kx plus omega t. If these two are related with the addition sign, that means a wave propagates in negative x direction. So this will be the situation, that if this is propagating, they are having omega t minus kx, or it could have a kx minus omega t, then it means it propagates in positive x direction. And if it is omega t plus kx, or kx plus omega t, then this wave will propagate in negative x direction. I hope this is clear. Is it clear? Do you understand this? Yes. So this is my standard relation. Y xt is equals to a sine omega t. It could be plus kx, it could be minus kx plus phi naught. I hope this is clear. Is it clear? Now do you have any doubts up till now? Great. So now let's look at the each part of this wave function one by one. So this is my standard relation of wave. It's a y xt is equals to a sine omega t plus minus kx plus phi naught. Yes, let's understand each term one by one. Amplitude A, it is the maximum displacement. It is the maximum displacement of any particle on the wave from its mean position in either of the direction, and that is what we call as the amplitude of the wave. So this is the maximum displacement that can be achieved by any particle on the wave from its mean position. Next is the phase, that is what we call as a phi. The phase of the harmonic wave is a quantity that gives a complete information of the wave at any time and at any position. So this is equals to phi, which is equals to omega t minus kx plus phi naught. And this phi naught is the initial phase. Next, it's a wavelength denoted by lambda. It is the distance covered by the wave during the time in which the particles of the medium completes one vibration about its mean position. It is something like this. If you remember the SHM, what we have decided is to complete a 4/4 means to complete a one oscillation. Yes. So let's say if someone says me that my vibration will start from here, then its vibration will be completed by here. So this is one of the wavelength. That is what we call as a lambda. But if someone asks me that no, my vibration will start from here, so what we are supposed to do is again a same thing. First, second, third and fourth. Yes. So it's his lambda will be over by here. If someone asks me that, let's suppose my vibrations will be begin from here, then his vibration will be ended up by here. It's a lambda again. So this is the situation where we are going to calculate the wavelength, and it is, we can say that it is the length of a one wave, or in a different word, it is the distance covered by the wave during the time in which the particle of the medium completes one vibration about its mean position. Next, it's an angular wave number or propagation constant k, or one more name, it's a wave number. Yes. So it's a quantity that is 2 pi by lambda. That is what we call as an angular wave number, and it represents the phase change per unit path difference, and its unit is radian per meter, or radian into meter inverse. This is what we call as a k, which is equals to 2 pi by lambda. Next, it is the time period t. It is the time period. It is the time in which a particle of the medium completes. It is the time in which particle of the medium completes one vibration about its mean position. That is what we call as a time period. And frequency, it is the number of waves produced per unit time in a given medium, is what we call as a frequency. And this frequency n, which is equals to 1 by t, which is equals to omega by 2 pi. It's unit of frequency. It's a second inverse, or we can say it's in hertz. And this is equals to t, which is equals to 2 pi by omega. I hope this is clear. Is it clear? Is it? Great. I hope this is clear. Next, it's an angular frequency omega. It is the rate of change of phase with time, is what we call as an angular frequency of the wave. For one complete time period t, the phase change is given as 2 pi by t, or we can say it's an omega is equals to 2 pi by t, which is equals to 2 pi f. It's radian into second inverse. Next, it's wave velocity. So when we define wave velocity, basically velocity, it is the distance traveled by one wave divided by time taken by one wave. So distance traveled by one wave, it's a lambda, and time taken by one wave, it's a t. So basically this is lambda by t, and we can have lambda into 1 by t. 1 by t is equals to frequency, so we can have this. It's a v is equals to, this is v is equals to f lambda. This is f lambda. F is the frequency and lambda is the wavelength. Or we can have one more relations too, that v is equals to lambda by t. If I divide and multiply this, it's a 2 pi by t multiplied by lambda by 2 pi. This 2 pi by t, it's the omega. 2 pi by lambda, it's a k. This is v is equals to omega by k. So this two relations can give me the wave velocity. I hope this is clear. Is it clear? So are you clear with every term that has been represented by plane harmonic progressive wave? Do you understand this? Have you? Are you sure? Are you sure? Do you have any doubts up till now? Do you? No? Great. So let's just summarize this very quickly, and then we will switch to the numericals. Please keep this noted. It's y is equals to a sine omega t plus minus kx plus, let's say, phi naught. In this relation, a is the amplitude, y, it's a displacement. It is the displacement of particle. Omega, it's an angular frequency, and when this omega, it's an angular frequency, this is omega is equals to 2 pi by capital T. This t is the time period. Next, we are having k, which is equals to wave number, and this k could have us, it's a 2 pi by lambda, and this lambda represents the wavelength of wave. Yes, and the phase phi is everything that we have written on the bracket of sine, or let's say it could be even cos. So this is at this point of time, it's an omega t plus minus kx plus phi naught. And if I have been asked initial phase, then it would be at t equals to 0, x equals to 0. It is the phi naught. Yes, have you noted this? Have you noted this? Great. Next, a wave velocity, which we denoted by v. This could be given as f lambda or omega by k. This is the wave velocity. And last but not the least, as in fact this is very important, thus if omega t plus kx or kx plus omega t, that means wave propagates in negative x direction and omega t minus kx or kx minus of omega t, it means a wave propagates in positive x direction. Yes, so these are the golden rules. These are the golden rules to get every numericals based on this. I hope this is clear. Is it clear? Please note this. Please note this. We are going to use this in our numericals. So have you noted this? Have you? Are you sure? Do you have any doubts up till now? Is there anything? No? Great. So let's have your pen and paper ready, and you are going to do this numericals with me. Let's look at the question. The question says that y is equals to 20 sine 4040 pi t minus 20 pi x represents a simple harmonic progressive wave. Find out its first amplitude, second angular frequency, third wave number, fourth sorry, wave velocity, next direction of propagation. Yes, first only this much. So let's begin, and please keep this doing very quickly. It's a y is equals to 20 sine 40 pi t minus of 20 pi x. Yes. So what I'm supposed to do is, this is a copy paste kind of question, and when we are having a copy paste kind of question, what we did even in the SHMs, that we just stick to our the master formula, and that master formula is y is equals to a sine, it's an omega t minus of k into x. So if this has been given, what I'm supposed to do is that amplitude a, which is equals to 20, omega, it's a 40 pi. Yes, you can see this, it is multiplied by t, it is multiplied by c. This is omega, which is equals to 40 pi, and if it's omega, it's equals to 45, it's a 2 pi by t, which is equals to 40 pi, and from this is equals to 2 pi, this is equals to 20. So it's a time period, it's a 1 by 20 seconds. I have not been asked the time period or the frequency, but if I'm about to find it out, its frequency would be equals to 20 hertz. I hope this is clear. Yes. Now let's find out the wave number k. This k, it's a 20 pi. Again, let's find out a wavelength 2. It's a 2 pi by lambda, which is equals to 20 pi. So this 2 pi, this is 10, and this lambda, which is equals to 1 by 10 meter, this is the lambda. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Great. So this is the wavelength which we can given, which we can return. It's a lambda, which is equals to 1 by 10 meter. So this is the wavelength. Next, what do we want? Yes, we want the wave velocity. So the wave velocity, which is equals to v, which could be written as omega by k. My omega was the 40 pi and the k was the 20 pi. So this is just the 2 meter per second. This is wave velocity. And last but not the least, it's a direction of propagation of wave. So if I want to find out the direction of propagation of wave, it is the relation that shows that it has having omega t minus of kx. So that means a wave propagates in negative, oh my mistake, it's a wave propagates in positive x direction. This is the direction of propagation of wave, because omega t and kx have been linked with a negative sign with each other. So my wave propagates in positive x direction. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Do you? Do you have any doubts? Is there anything? No? Great. Next, let's work for the next question. Y is equals to minus 10 sine 2 pi into bracket 80 minus 4x represents simple harmonic progressive wave. Find out first, again all these things, it's an amplitude. Second, wavelength. Next, time period. Next, wave velocity. Next, initial phase. Yes, let's find out these things. So a relation that has been given by the data, it's y is equals to minus of 10 sine 2 pi into bracket 8t minus of 4x. So first thing what I understand is this 2 pi should be shifted into the bracket. Why? Because my standard relation, if you see the standard relation, it's a y is equals to a sine omega t minus of kx. Yes, so there is nothing written after the sign. So please shift this 2 pi to this bracket. So if I am going to shift this, it is simply the y is equals to minus of 10 sine, multiply this 2 pi over here, it's a 2 pi into 8, which is 60 pi into t, minus of 2 pi into 4, it's an 8 pi x. Yes, great. Another variation is this is a, which one is positive, here minus negative sign is there, and this is a function of sign. We know that anything that lie into the third quadrant which is equals to a 180 plus theta would be a negative for the sine, because in the third quadrant 10 is positive, that we have discussed. So this could be written as y is equals to 10 sine 16 pi t minus 8 pi x plus pi. I hope this is clear. Is it clear? So this is equals to y, which is equals to 10 sine 16 pi t minus of 8 pi x plus pi. This is the situation. Now you can relate this with our standard relation, which is equals to y, which is equals to a sine omega t minus of kx plus phi naught. I hope this is clear. And now you can have everything. Let's do it quickly, very quickly. Please do it fast. That amplitude a, which is equals to 10, omega, which is equals to 16 pi. If I have been asked time period, it's a 2 pi by t, it's a 16 pi. This is t, which is equals to 1 by 8 seconds. Frequency, it's an 8 hertz or second inverse. Now wave propagation constant k, which is equals to 8 pi, and from this it's a 2 pi by lambda, which is equals to 8 pi. This has gone, and lambda, which is equals to 1 by 4 meter inverse. I hope this is clear. Next, wave velocity, which is equals to omega by k, and this wave velocity omega by k, it's a 16 pi by 8 pi, which is equals to 2 meter per second. And direction of propagation, that this wave propagates in positive x direction. So this wave propagates in positive x direction. And next, it's a phase, or I should say initial phase, is the pi radian. I hope this is clear. So this is the initial phase which we can say it's a pi radian. I hope this is clear. Is it? Do you have any doubts, any queries up till now? No? Great. Now let's define two new words, two new terms for us, which is particle velocity and particle acceleration. So we have the relation which says that y is equals to a sine omega t plus minus kx. Let's say phi naught is the 0. So this is the relation. If you understand this y, this is the displacement, but this is displacement of particle. This is not a displacement of a wave. Wave travels, wave does not displace. I hope you understand the difference between these two. Only the particles of the medium that oscillates, or we can say they displace, or they are having a oscillatory motion about their mean position. So if I want a velocity of a particle, what I need to do is I need to just differentiate this with respect to time. So this is particle velocity, which is equals to d by dt of y. This is equals to d by dt of a sine omega t plus minus kx. So this is equals to a omega cos omega t plus minus kx, and the maximum particle velocity, this vp max, if I want, then this term, it's an omega t plus minus kx, should be 1. So this vp max could be given as a omega, because this is equals to 1. This is vp max. Now if I want a particle acceleration, then I need to again differentiate this. With one more time, and that could be given as ap. This is equals to d by dt of vp, which is equals to d by dt of vp, it's an a omega cos omega t plus minus kx. This is equals to a omega as it is. It's a minus of sine omega t plus kx multiplied by omega. So this is equals to minus of omega square into bracket a into sine of omega t plus minus kx. Yes, I hope this is clear. This is how we could get uh, acceleration of the particle and velocity of the particle. I hope this is clear. Now, if someone has asked me that find out ratio of find out ratio of wave velocity to maximum particle velocity. If someone asks me that find out the ratio of the wave velocity to the maximum particle velocity. So for me it's v wave is equals to omega by k, and maximum particle velocity it's a vp max, which is equals to a into omega. If I take a ratio of this two, then it is the v wave divided by this is vp max. This is equals to omega by k into 1 by a omega. It's 1 by ak. Or if it is vp max to the v wave, then this is equals to a into k. I hope this is clear. So this is the maximum particle velocity. This is the maximum particle velocity divide by wave velocity, which is the ratio of the, or which is just the multiplication of the a into k. I hope this is clear. Is it clear? Please note this. We are going to have a question based on this. Did you noted this? Did you? Are you sure? Have you noted this? Great. So now let's work for the question. Suppose the question says that y is equals to phi sine 400 pi t minus 300 pi x plus pi by 4 represents a simple harmonic progressive wave, then find out first particle velocity, next maximum particle velocity, next particle acceleration, next it's a vp max, maximum particle velocity to the wave velocity. I hope this is clear. So let's do it quickly. We have given the relation which is equals to y, which is equals to phi sine 400 pi t minus of 300 pi x plus pi by 4. And what I want first, I want a particle velocity. So let's just differentiate this. This is vy, which is equals to phi into sine would be the cos, which is equals to 400 pi t minus of 300 pi into x plus pi by 4, and this pi would be the multiplied, it's a phi into 400 pi because it's an a omega. This is the particle velocity, I should say it's a vp. I hope this is clear. Second would be the vp max, which is equals to a omega. So it's a phi into 400 pi, which is equals to 2000 pi meter per second. This is the vp max. Next, it's an acceleration, or we should say a particle acceleration. This could be given as this is phi into 400, which is equals to 2000 pi. I'm going to differentiate this. Let's have a look. It's a cos, that would be minus of sine 400 pi t minus 300 pi x plus pi by 4 multiplied by this 400 pi. This is 2000, sorry. Yes, so this is equals to 2 into 4, 8 into 3 and 2. It's 8 into 10 to the power 5 pi square minus of sine, it's a 400 pi t minus of 300 pi x plus pi by 4. This is the relation of the particle acceleration. This is particle acceleration. I hope this is clear. Have you got this? Have you? Do you have any doubts up till now? Is there anything? Is there anything? No? Great. So this is particle acceleration. This is the particle acceleration. Now what I want the ratio. I want the ratio of the particle velocity to the wave velocity, maximum particle velocity to the wave velocity. So this will be Vp max to the V wave, and this Vp max, it's a 2000 pi divide by V wave, it's a omega by k. Yes, so it's a 2000 pi divide by omega of this, it's a 400 pi multiplied by k, that is equals to 300 pi. So this is 400 phi 2000, it's a 5, and this is equals to 1500 pi. Yes, as it is a ratio of the same quantities, it could not have any units. I hope you understand this. Do you? Great. So is it clear? Is it absolutely clear? Do you understand this, or do you have any doubts? Any doubts up till now? Is there anything? Is there? No? Great. So now let's work for the next question. If maximum particle velocity is twice the wave velocity and amplitude of given wave is 5 units, find out wavelength of wave. So how will we do this? They said a maximum particle velocity is twice the wave velocity, and amplitude of given wave is 5 units. We need to find out the wavelength of the wave. So this is Vp max divided by V wave, which is equals to A into K. And as they said that maximum particle velocity is twice the wave velocity, this is equals to 2 is equals to A multiplied by K, which is 2 pi by lambda. So it's a lambda which is equals to this has gone. Lambda is equals to pi into a, and amplitude is 5 units. It's a 5 into pi meter. This will be the final answer. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Is there anything? Do you have any doubts up till now? Is there anything? No? Great. Now, let's define a relation between phase difference and path difference. Let's suppose consider the 2 points. They are at the positions x1 and x2 on a wave at a given instant, and in phase of the first wave it's an omega t minus of k into x1, and phase of the second wave it's an omega t minus of k into x2. So their phase difference, it's a phi 1 minus phi 2, that is equals to k into bracket x2 minus x1. If phi 1 minus phi 2 could be written as delta phi, then this x2 minus x1 could written as delta x. This is what we call as the phase difference, and this delta x is said as the path difference. Yes, so delta phi, it's a phase difference, and delta x, it's a path difference. So this is the situation, that this is the relation between phase difference and path difference. I hope this is clear. So delta phi, that would be equals to 2 pi by lambda multiplied by delta x. Now let's understood that how do we use this relations. Let's have a look. Suppose this is the one wave. As you can understand that this is completion of 4 quarters, so it represents the one wave. Yes, this is the wavelength that we know, it's the length of one wave. This is the lambda by 2, it's because it is the half of the wave. This is the lambda by 4, it's half of the wave. And if you measure a distance from this O, then this distance, it's 3 lambda by 4. Yes, because they are going to complete 3 quarters from this from the 4 quarters. Yes. So let's suppose if someone asks me something like this, that let's have a look, that one of the particle is at here, it is at A sorry, and other particle is at here. Yes, if they ask me find out phase difference between A and B, this is the requirement. You need to find out a phase difference. You need to find out phase difference between A and B. How will you do this? So what we should understand is that we know delta phi, which is equals to 2 pi by lambda into delta x. So for this it's an x2 which is equals to 3 lambda by 4, and it is at the beginning position, so this x1 equals to 0. So first let's calculate delta x, and this delta x which is equals to 3 lambda by 4 minus of 0 which is equals to 3 lambda by 4. This is the path difference, and what I need to do, it's in delta phi is equals to 2 pi by lambda into delta x. This is equals to 2 pi by lambda multiplied by delta x, which is equals to 3 lambda by 4. This lambda has been gone, and this is equals to 3 pi by 2 radian. This is equals to delta phi. So this delta phi, which should be this delta phi could be written as 3 pi by 2 radian. I hope this is clear. Is it clear? Is it clear? Great. So this is the delta phi, which we call as the phase difference between this two. It's a delta phi which is equals to 3 pi by 2 radian. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Is there any doubts? No? Great and well done. Now let's let's do a one more question based on this. Let's suppose they have given that one of the particle is at here and this distance is lambda by 8, and let's say another particle is at here. So this is particle A, this is particle B. They have asked us find out phase difference between particle A and B. Find out phase difference between particle A and B. Yes, so this is the lambda by 2 and this is at lambda by 8. First requirement is to find out the path difference. This is equals to delta x. This is equals to lambda by 2 minus of lambda by 8, and this is equals to 4 lambda by 8 minus of lambda by 8. This is equals to 3 lambda by 8. This is equals to path difference delta x. Next, it's a delta phi, that is equals to 2 pi by lambda into delta x. So this delta x would be given as 3 lambda by 8. This is equals to 2 pi by lambda multiplied by 3 lambda by 8. This lambda gone. This has gone, and this is equals to 3 pi by 4 radian. I hope this is clear. Is it clear? Is it? Are you sure? Great. So do you understand this completely? One more question. One more. Great. Let's have a look. The question says that find out phase difference between two particles. Find out phase difference between two particles. They oscillates on two different ends of one wave. Yes, this is the requirement. They said find out phase difference between two particles. They oscillates on two different ends of one wave. So first let's have a photo of this, that how this should look alike. And probably this is the wave, and one of the particle would be oscillating at here and another is the oscillating at here, because this is the one end of the wave and this is the other end of the wave, and this is the lambda. Yes, so this x2 it is at lambda, it's an x1 which is at 0, and this path difference would be equals to lambda minus of 0 which is equals to lambda. So it's in delta phi, which could be given as 2 pi by lambda into delta x, and this is equals to 2 pi by lambda into delta x. Delta x is the lambda, this has gone, and this is equals to 2 pi radian. This is delta phi. This is equals to 2 pi radian. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Do you have any doubts? No? Great. So this is delta phi. which could be given me the 2 pi radian. So this is basically a difference. This is basically a relation between the path difference and phase difference. Now let's define one more difference, which is a relation between a phase difference and a time difference. Let's suppose one of the wave is having the phase something like this, which is equals to omega into t1 plus kx, and one another wave it's having a phase which says it's omega into t2 plus kx. If I find out the phase difference, which let's say it's a phi 2 minus of phi 1, and then it could be said that's an omega t2 plus kx minus omega t1 plus kx. This kx has gone, and I have been left with the omega into bracket t2 minus of t1, and this is delta phi. So this delta phi would be equals to omega could be replaced by 2 pi by t, and this is t2 minus t1. This is what we call as a delta t. Here delta t, it is the time difference. So this is the relation, this is the relation between a phase difference and time difference. This is the relation between phase difference and time difference. I hope this is clear. Is it clear? Are you sure? Do you have any doubts? Do you have any doubts? Is there anything? No? Great. Now let's have a question based on this. Let's say this is the wave, and we know that this is the time period t. This is half of the time period, it's a t by 2. This is 1/4 of the time period, this is t by 4. This is, if I have been considered it from here, this is 3t by 4. Yes, I hope this is clear. Is it clear? This is 3t by 4. Is it? Great. Now let's suppose I have been given something like this, that your one of the particle is here, it's an A, and another particle is at here. That find out phase difference between points A and B. So basically this is t by 4 and this is 3t by 4. So let's calculate the time difference, and this time difference could be given as delta t, which is equals to 3t by 4 minus of t by 4, which stands for 2t by 4, and this is equals to t by 2. So this will be delta phi, which is equals to 2 pi by lambda into delta t, and this could be given as it's a 2 pi by lambda into delta t, which is equals to, it is, oh sorry, it's a delta phi which is equals to 2 pi by capital T into delta t. It's a 2 pi by t into delta t, and this delta t, it's a t by 2. This has gone, it's a 2 pi by 2, which is equals to pi radian. I hope this is clear. Is it clear? Yes. So this is how we can relate a phase difference and time difference. Let's have one more question based on this, and this will give us the confidence. Let's suppose they have given one wave, and they said that time to complete this much portion of wave is, let's say, 5 seconds. We have two different particles, you can see it here. This is particle A, this is particle B. They said that particles A and B, let me rewrite, particles A and B are separated by 2 milliseconds. Find out phase difference between this two particles. We need to find out a phase difference between these two particles, and these two particles are separated by 2 milliseconds. How will you do this? What could be done? So what relation I am having it? It's a delta phi, which is equals to 2 pi by t into delta t. This delta t they have clearly mentioned. It's a 2 millisecond. So it's a 2 into 10 to the power minus of 3 seconds. But what about the time period? This is 5 seconds and this is just t by 2. I hope you understand this. So if this is t by 2, or what I want a t, it's a t by 2 which is equals to 5 seconds. So from this it's a t which is equals to 10 seconds. So put up the value and get the data done. It is the delta phi which is equals to 2 pi by 10 multiplied by delta t which is equals to 2 into 10 to the power minus of 3. So this is equals to 2 pi 2, so it's 4 pi into 10 to the power minus of 3 divided by 10, which is equals to 0.4 pi to 10 to the power minus of 3 radian. I hope this is clear. Is it clear? Are you sure? Are you sure? Great. Now let's look at certain quick questions. The question says progressive waves are waves which blank travel in a given direction, which continuously travel in a given direction. Next, second question, which of the given physical quantity related to the particle in wave motion continuously changes? Yes, phase of the wave continuously changes. I hope this is clear. Is it? Great. So let's wind up this session over here. This was the introductory session of the wave, as well as we have covered the plane progressive wave. Please go through this very carefully, because if you observe and if you look at the previous year asked questions, you will definitely find one of the questions from the waves from this segment only. So please do this. Please revise this, and please attempt as many questions as possible from this segment. Thank you. Have a good day. Take care.